Good morning, good afternoon, good evening, wherever you may be in the world. Welcome to my second presentation. And my second presentation is titled Types of Wind Turbines and Forthright Through Techniques that are applicable to these wind turbines. My full name is John Kuku Amaotu, and I have 30 years experience as an electrical engineer in medium voltage, high voltage, and low voltage. Next, let's talk about the next slide. We talk about the existing challenges for the current energy sources that we have. As you know, the current energy power producing sources that we have, or the traditional energy sources we have, from coal plants, gas plants, oil plants, and nuclear power plants. As you know, when these energy sources are utilized to produce electric power, what happens? It results in production of pollutants into the atmosphere. It also results in a lot of emission of carbon dioxide into the atmosphere. And after these, power producing energy sources that produce a lot of carbon dioxide into the atmosphere, it results in global warming concerns. You know, and basically, as many nations are basically fighting for climatic change, they've basically come with an accord called the Paris Accord, and the goal is basically to limit that temperature rise within less than 1.5 degrees. As such, many nations, their goal is basically to reduce carbon dioxide emissions by 80% by the year of 2030, and also, achieve a net zero carbon reduction of basically zero, in the year 2050. As such, many nations and many utilities are shifting to alternative means of energy production, and the good choice is renewable power plants. And out of the renewable power plants, we have hydro plants, and hydro plants have been in existence for many uh, years, many decades, more in fact over more than 100 years. And actually, power production started from hydro power plants. Next is wind and solar PV, and basically that's a great figure. These days, that is there's a high penetration of wind and solar PVs into the existing AC network. Next is the biomass. Biomass basically is production of electrical power utilizing trash, basically, basically tie um, waste, and basically, that goes to, the boiler process, to generate the required heat to heat the water, and steam out of the water basically is used basically to feed steam turbines. Next is geothermal, and what does geothermal um, power production means? It means that we are harvesting or harnessing, the embedded heat, the inherent heat that is below the Earth's surface to basically form steam. And that steam is basically, fed to a steam turbine. Next is ocean tidal waves. As you know, we have many oceans across the globe. We have the Atlantic Ocean, we have the Indian Ocean, we have the Pacific Ocean, and we have the Baltic Sea, and we have the North Sea. These, seas and oceans have very high tide, especially when you go to the deep side of these oceans. And aside when these tidal waves basically emerge, basically it has a lot of energy, and there's a need to harvest that energy from these tidal waves to produce electric power. Now let's talk about what is wind power and the components of wind power. Next is the types of wind turbines that we have and the driving technology that drives these wind turbines. Next is typical turbine rating that we have for onshore and offshore wind farms. Then we'll talk about the components of the wind turbines and the power characteristics of the wind turbine. Then the different types of the wind turbines that we have. Actually, we have four major types of wind turbines. And a typical installation of onshore or offshore wind turbine. Basically, they have different installation procedures and guidelines, and I will go through that. Next is wind turbine protection. That is the inherent wind turbine protection that each wind turbine has. And on a holistic level, on a whole wind farm level, there are also protection and proprietary techniques that each wind farm is supposed to have to stay connected to the grid during disturbances on the network. So basically, this leads us to grid code. Next, we'll discuss the challenges that the existing wind farms due to the high penetration of different database resources. Many of them are penetrating to the existing ACCs. It basically results in a lot of challenges, and we'll talk about that challenges and how we are mitigating those challenges. Next, we'll talk about what is a wind power, right? Okay, wind power is basically, providing the platform and the basis, to be able to put in the right equipment to be able to harvest or harness the power energy based on these wind turbines that have been formed in a cluster of configuration and arranged in different, arrangements and integrated to the AC grid at a point of common coupling. These wind farms can operate in a connected mode. And what does connected when it is operating in a connected mode? Connected mode means that it is connected to the AC grid. And when it is operating in an island mode means that it is not connected to the AC grid. And basically, it is providing power to locally, to local load. Now let's talk about the components of the wind turbine. A wind turbine has a blade, and most often than not, the horizontal type has a three blades. And basically, these blades turn when the wind with a speed basically impinges on it. So we have something we call a cutting speed at 4 miles per second. That's the wind velocity. So that is when the wind turbine cuts in and starts generating electric power. And so it follows the curve. It's based on the cubic, of the wind velocity, v cube. And so it reaches the rated speed. And the rated speed is basically, it hovers around 11 miles per second to 12 miles per second. Then, as you know, definitely, we have wind gas, and so when wind gas sets in, we need to protect this wind turbine. So, it has been basically, programmed and researched and found that, at wind speeds of 20 to 25 miles per second, it is time to shut off the wind turbine and prevent damage, and that prevents damage to this wind turbine. Next is regulation of the speed of the rotor of the turbine and the rotor of the generator. There has to be a way of controlling the speed of these shafts, right? So we utilize the pitch angle of the wind turbine blades to achieve this phenomenon. As such, how do you rotate the blade to achieve to adjust the pitch angle? We rotate the blade in a longitudinal axis. Next is the mechanical drive train gear system, and basically the mechanical components of the wind turbine basically consist of, a slow speed of shaft and the gear system. And what is the purpose of the gear system? Right? The gear system is basically to convert very low revolution per minute of the low speed shaft. And if it goes through the gear system, it is multiplied by between 1,000 to 2,000 times to achieve a higher speed. Right? That is required by the generator to generate the required electric power to form a wind farm and basically integrate it to the grid. Next is the power electronics component, which is formed in the back-to-back. And if I say back-to-back, what does it mean? Back-to-back means that you have a wind turbine that generates power in the AC mode, right? Okay, so it is converted from AC to DC by the front end converter, or also called a machine side converter or the rotor side converter. Then this DC power is stored on a DC link that has an embedded capacitor that stores basically the charges to maintain the DC voltage. On the other side, the grid side converter, basically its purpose is to basically invert the DC voltage or the DC power back to an AC power before it is integrated to the AC grid. So, as such, this applies to two different types of wind turbines. And what are they? The double-fed induction generator, and basically this utilizes 30% power rating back-to-back converter. And for the permanent synchronous generator, it utilizes a full scale, 100% power back-to-back converter. Next is a step-up transformer. And what is the purpose of the step-up transformer? The step-up transformer basically sets the output voltage of each wind turbine. And most often than not, the output voltage of each wind turbine is 690 volts, right? To achieve efficiency reliably, right, we need to step up the voltage, and that is the purpose of stepping up voltage and transmitting it at a higher voltage. So this step-up transformer steps the voltage up from 690 volts to 33 kV AC collection voltage or 56 kV AC collection voltage. Currently, most installations are shifting from 33 kV AC collection voltage to 66 kV AC collection voltage, and the reason being that is because of efficiency and lower cost in terms of maintenance because you have less array of cables, right? Okay, so now let's talk about the location of the step-up transformer. For onshore facilities, onshore wind farms, right, wind turbines, the step-up transformer is located right in close proximity to the wind turbine. And for offshore facilities, right, definitely we cannot have the step-up transformer, located on, the ocean. So basically, the step-up transformer is located at the bottom of the wind turbine. Next is the control scheme. Yes, definitely. You need a control scheme that is basically will control the power electronic converters and also the blades of the wind turbine. Next, we talk about the types of wind turbines and the driving technology that drives these wind turbines. First is the square cage induction generator. And this generator operates on a fixed speed, and the fixed speed is dictated by the grid frequency. And the evolution of wind turbine actually started from this type of wind turbine generator. Next is induction generator. Right? This induction generator basically helps us to achieve a little bit of room for variable speed operation. And the operating range is plus or minus 10%. And this is achieved by external resistors that have been integrated into the one rotor winding. Next is a synchronous generator, and that is a permanent synchronous generator that utilizes a full-scale converter, power electronics converter, that is arranged in the back-to-back configuration. Next is double-fed induction generator, and like I made mention, this helps us to achieve a variable speed drive and also pitch regulation and pitch variation, utilizing 30% back-to-back, converters. Now let's talk about a typical turbine rating, and this basically a lot of questions comes from this that on what is a typical onshore wind turbine rating and a typical offshore wind turbine rating. For onshore wind turbine rating, the current ratings basically ranges from 2.3 megawatts to 3.5 megawatts. The reason why we have such a rating is because onshore facilities, because you have a lot of households, and basically your goal is basically to minimize the visual impact of these wind turbines. And also, as these wind turbines operate, they emit a lot of noise, and your goal is basically to minimize it. And as you go with a lower rating of a wind turbine, basically the noise emission is mitigated or lowered. Next, let's talk about the typical ratings for offshore wind turbine facilities, and that ranges from 2.3 megawatts to 14 megawatts. So, comparably or invariably, compared to offshore wind farm facilities, the wind turbines have a higher rating. And what is the reason why they have a higher rating? Is because offshore wind farms are located in very remote locations, very far from living, areas. And also large acreage of sea for us to basically install these. And basically it can accommodate a higher rating. And in terms of basically the noise emission, there's no living conditions there. So as such, we tell us about, having a large rating of a wind turbine that can make a lot of noise. And also, the goal is basically, to leverage on that large acreage to basically achieve a higher wind farm rating. Now let's talk about the evolution of wind turbines, right? Okay, so this actually came from Siemens Gamesa, and wind farms actually, as you can see the picture on my left, right? Okay, you have total height from blade tip to the bottom of the ocean, and that is 59 megawatts. And this wind turbine is rated at 0.45 megawatts. As you can see, it's even less than 1 megawatts. And the rotor diameter is about 18 meters. Now let's talk about the bottom, side of the wind turbine. It's about only 5 meters. Right? Okay. Next, it's evolved to a 9.5 megawatts wind turbine. And this time, it has a rotor diameter of 164 meters. As you can see, look at the big difference from 80 meters to a big jump to 164 meters. And the height from the bottom to the tip is about 267 meters. And definitely, they went from 5 meters to 39 meters on the depth, the water depth. Next is the next evolution, and this time they went to 12 megawatts, and that was about a couple of years ago. So, and these were installed at Doggerbank wind farm, in 2021. And this is a typical picture of the GE Hollywood, and the rotor diameter is about 220 meters. This is huge. And the height from the bottom of the ocean to the tip of the blade is about 304 meters. Okay, so next is the most current, and this actually came from Siemens Gamesa, and we have a wind turbine that is rated at 14 megawatts, right? Okay, so what is the rotor diameter? This time they went to 222 meters, and the height from the bottom of the ocean is 324 meters, and the water depth is about 43 meters. Okay, so basically, as you can see, all these giant structures, right? What do? Basically comparing it with the Eiffel Tower, as you can see, then giant structures are getting closer to the Eiffel Tower. And for the Eiffel Tower, we have a height of 324 meters. So basically, the height of this wind turbine, actually the latest one, the 14 megawatts, is quite close to the height of the Eiffel Tower. Now let's talk about the types of wind turbines that we have. We have the vertical axis wind turbines and the horizontal axis wind turbines. Okay, so as you can see the picture on my right side, okay, this is an example of vertical axis wind turbines. Actually, the evolution of wind turbines started from the vertical axis wind turbines. Yeah, and this is a picture of a modern vertical axis wind turbine based on improvements in technology. Then we have the horizontal axis wind turbine, and that is many of the wind turbines that you see at onshore location and offshore location. Now let's dive deeper into what vertical axis wind turbine looks like. For a vertical axis wind turbine, definitely, the generator is located at the bottom, right here, okay? Compared to a horizontal axis wind turbine, where the generator and the turbines are located at an enclosure called a nostril, right? So that is the difference. Such, we don't have that huge structure of nostril for the offshore wind farms or the other horizontal axis wind farms where the nostril is located here. Next, it's much lighter in weight. Definitely, if you don't have that huge, blades and nostril, and those wind turbines located on top, definitely this structure is going to be lighter compared to the horizontal axis wind turbine. Also, there is no yaw or pitch control system. You know, like I made mention, you know, the yaw and the pitch control system is utilized in the horizontal axis wind turbine. And what is the goal that we use there? We utilize the yaw system basically to redirect the blade when the wind direction changes. And also, we utilize the pitch control system, to regulate the speed of the shaft of the turbine and the generator. Also, less mechanical structures, as you can see from the picture. If you compare this picture to the wing and the horizontal axis wind turbine, it's not like, okay, you can see that definitely we have a less mechanical structure. For installation, maintenance, operation, it is much easier. As you can see from the picture, less mechanical structures comparably, definitely there's going to be less, it's going to be much easier to install and operate and maintain this type of wind turbine. In terms of structural loading, as you can see from the picture, less mechanical members and structures, so definitely the structural loading is less and much reduced comparably. Okay, so as we all have a goal to basically improve more on efficiency and have a reduction in maintenance. So that is why in certain locations, investors and basically developers choose to go that route of utilizing vertical axis wind turbines. Then, like I made mention, we have a reduction in maintenance costs invariably, comparably. Then the only drawback, right, is let's say if you have a high wind gust, when you have a turbulence, because the generator is located here. You have a lot of wear and tear. And also you the blade root. Basically, you have wear and tear right here. This is the root of the blade. That's where it is located. Now let's talk about horizontal axis wind turbine. And like I made mention, this is the most common type of wind turbine that we have. And its purpose, basically, and matter of fact, for all wind turbine is to convert kinetic energy into mechanical energy and thence to electrical energy. They are the most dominant, like I made mention in recent days. in wind power plants or wind farms. Okay, so now these are typical pictures of horizontal axis wind turbine. In a slide before, I showed you pictures of what a vertical axis wind turbine looks like. So as you can see, this is what they call horizontal axis wind turbine, and this is a fixed bottom type, vertical horizontal axis wind turbine. The reason why it is called fixed bottom is because the structural supporting these wind turbines is fixed to the bottom of the ocean or the seabed. And this is a typical picture of five wind turbines that is, located in the Block Island area that provides electricity to the households over here. And this is basically, another picture of horizontal axis wind turbine. And basically, it's basically utilizing an energy island to basically distribute the um, wind power that is harvested from this wind turbine. Next is another picture of what a horizontal axis wind turbine looks like in a typical sea environment or ocean environment. And and as you can see over here, this is the typical substations where the collectively, where the harnessed power is basically, it goes through, all this sort of all the power electronics converters that basically changes for the transmission level, changes the AC to DC before it is transmitted through the subsea cable to onshore facilities. Next is another picture of horizontal axis wind turbine. But this time, the picture on my left shows you a typical horizontal axis wind turbine that is located at onshore facilities. And next on the right is a typical horizontal axis wind turbine that is located at offshore facility with a fixed bottom. As you can see, the bottom structural element is located, is fixed to the bottom of the ocean. Next is a picture of the components of the wind turbine. As I indicated, you need a gear system, right, to basically multiply the speed of the low shaft on the turbine side, to basically increase the speed to the rate of the speed that is required by the rotor of the generator. So this is a typical picture of what the gearbox looks like, the gear system looks like within a wind turbine. Next is continuing with the components of the wind turbine. Remember I made mention of the yaw mechanism, the yaw system. And what is the yaw system? I will basically, re-emphasize. It helps the blades to realign if the speed, the wind speed direction changes. So it has a lot of several motors. As you can see, these are the motors that we have that helps the wind turbine blade and the hub to change, to move, to realign with the new directions. And below that is the velocity sensor, and basically that senses the wind velocity and wind speed. It's a picture of what a typical wind turbine blade. As you can see, these are massive, and look at the way it is transported, and you have in this picture you can see you have two trucks, basically one on the other end, one on the other end, and basically they transport these blades in a coordinated fashion, and for each wind turbine you need three blades, so you can see that this is done in three different arrangements, two trucks for each blade. Next, we'll talk about the power curve. Remember, I made mention that basically, the power curve is what helps us to basically see the various operating portions of the wind turbine, right? Okay, so the operating regions of the wind turbines, we have a cutting speed, right? Okay, so up, right at, basically you energize a wind turbine and the wind start blowing, when it reaches the cutting speed, and usually for most wind turbines, we have 4 meters per second as the wind velocity that is required for the wind turbine to start generating power. So cutting speed is when the wind turbine starts generating power based on this curve, and this is based on the cubic velocity of the wind speed. And the curve on the left hand side is basically the power that is in the wind itself, right? Okay, and on the right is basically the power that is generated by the wind turbine. So as it starts increasing its power based on the cubic value of the wind velocity, it reaches rate speed. Okay, and at rate speed, that is when it basically generates the required rated power. So let's say for a 14 megawatts wind turbine at the rated speed, that is when it's able to generate 14 megawatts. For a 5 megawatts wind turbine at the rated speed, that is when it is able to generate the rated power of the wind turbine at 5 megawatts. So, at times we have, wind gas, and sometimes, you don't want the wind turbines to basically be exposed to this high wind. And this wind gas can range between 20 to 25 meters per second. Right? Okay, so the other portion of this power curve is called cutoff speed. Okay, so that is the point that basically shuts down the wind turbine, to avoid excessive mechanical stresses and damage to the wind turbine. Now let's talk about the different control blocks of power blocks of the wind turbine. Okay, so basically there's something they call the aerodynamic block right over here, and the mechanical block and the electrical block, right? Okay, so the aerodynamic block is basically the blade section, right? It's operating in aerodynamic mode, just like an airplane, when, so basically you have the wind speed coming in as an input, right? Okay, so there's something they call tip speed ratio calculation, and the tip speed ratio is the ratio of the angular rotation of the rotor times the radius of the rotor, that is WR, over the wind speed. That gives us the tip speed ratio calculation. Okay, so that is a lambda. Its value is a lambda, right? Okay, and that becomes an input in calculating the rotor power coefficient, CP. In addition to that, the other input is the pitch angle. Remember I made mention that we control the pitch angle to control the speed of the rotor, the turbine shaft, the low speed shaft, and the high speed shaft, right? Okay, so having alpha and beta as an input variable quantities to the in calculating the rotor coefficient CT, we can calculate the aerodynamic torque utilizing the angular velocity of the rotor. Right. Okay. So after calculating that torque, that becomes an input into the mechanical block, and that can be modeled as two-mass shaft, including the gearbox, and this becomes an input to the electrical block and the induction generator. So basically, the angular rotation of the generator becomes an input to the induction generator. Then basically the electrical power is generated back to the grid. Next, we'll talk about the power equation of the wind turbine, right? Okay, so like I told you that we have the wind turbine blades, right? And we have three of them. And what is the purpose of the wind turbine? Basically, its goal is to basically harvest all the wind energy or the kinetic energy and convert them to mechanical energy. Then from mechanical energy, it is converted to electrical energy utilizing the induction generator. Right. Okay. So there's a lot of energy transformation, as you can see, from kinetic to mechanical to electrical. So Let's talk about what the value of the kinetic energy. As you know, kinetic energy is half mv squared, right? So half times the mass of the rotor times the wind velocity, right? So that's half mv squared. And what is power, right? It's the rate of change of energy with time. Okay, so it's kinetic energy over time, and the final equation is half mv squared over t. Right? So from the equation, right, we can m over t, we can equate it as a mass flow rate, right? So what is the mass, right? We can equate a mass as an area times length times the density of the wind, right? Okay, so this is the value of mass. Over time, this is the equation we can achieve, right? Area times length is basically uh, velocity, right? So we have AV times rho, which is density, right? So we can put this back into the equation, and this is the final equation that we have. Half times the area, the swept area, times the density of the wind, times the velocity of the wind here. So this is the power of the harvested wind. And this is based on transformation of energy from kinetic energy all the way to electric energy. Right. So next, we'll talk about what the different types of wind turbines we have. And the first one is the fixed speed type, type A, or type 1 wind turbine. And basically, this is what started the evolution of wind turbines early 1990s, and it operates as a conventional voltage induction generator, and has a fixed speed. You know. And for such an induction generator, right, when you are energizing the generator, there's something called inrush. It has a very high inrush, 50 times the nominal current. As such, to control the inrush, what do? We utilize an electronic starter, stop starter, to basically control the speed of the generator. As such, consequently, we are controlling and basically, decreasing the inrush as basically, we bring the generator up to speed. This wind turbine is basically, it goes through a separate transformer, and basically sets the voltage up before it is integrated to the AC grid. Like I made mention that it has a fixed speed, and how does the fixed speed come about? Because the fixed speed is regulated by or dictated by the frequency of the gauge. So any changes in wind speed will not affect the rotational speed. Because the speed is fixed by the grid or dictated by the grid. Also, because of the reactive power requirement, it's to maintain the AC voltage, it requires that amount of reactive power support, and basically this can be achieved by reactive power compensation by installing capacitors. You can also install static power compensated at the point of common coupling, or you can also install STATCOM, static synchronous compensators at the point of common coupling to support basically the voltage regulation at that point. It is very simple and very robust in construction. It requires a strong grade, you know, or a stiff grade. And when we say a strong grade or a stiff grade, what does it mean? It is a grade that has a high amount of short circuit current capability. That is affect changes, when a fault occurs that basically, generates a lot of current, it doesn't result in, basically, changes, large changes in voltage, basically the voltage is very safe, yeah. The cost is much lower because it's very simple, and does not have a lot of components, and Like I made mention, it draws a very large starting current, and basically you utilize the electronic starter to control this starting current. It has a lower energy conversion, and as such, overall efficiency is very low. And I made mention that any changes in the wind velocity, it's not basically reflected on the gauge. It won't change because it's a gauge that dictates the speed of this. And also, there's a lot of excessive mechanical stress, and it can also have significant fluctuation in its output temperature to the indicated gauge. Matter of fact, because of all these inherent drawbacks associated with this type of wind turbines, it cannot be used in a large capacity wind farms. Let's say if we have a large farm array that we want, we cannot use it. Most of these are utilizing a very small, very very small wind farm configuration. Next is the variable speed wind turbine, which has a limited variable speed or the type B or the type C. So as we implement a variable speed operations philosophy into this wind turbine energy conversion system, basically it helps us achieve much more efficiency comparably. So this wind turbine compares to the fixed type A, this has a much more efficiency inbuilt into it, and also has much more aerodynamic capability than the type A. And also, the mechanical stresses are reduced due to the inherent variable speed operations that can be achieved. And the slip control is about plus or minus 10%, and the speed variation is about plus or minus 10%. And because the mechanical stresses can be reduced due to the variable speed operations that can be achieved due to the inherent, variable resistance that is integrated into the rotor winding, it helps us to reduce the wear and tear and also the gearbox maintenance. Like I made mention that it has external resistors, and these resistors that are integrated and connected to the rotor circuit allows us to basically achieve the variable speed operation. And with this variable speed basically control the rotor current, and as such control the speed of the generator. It requires a reactive power, and basically, I'll say that, the reactive power requirement is on a lower scale compared to the type A, and it also requires a gearbox. I'll say that, just like the type A, not ideal choice for large wind farm realization, I mean, you can implement this type of wind turbine in a smaller wind farm realization. Now let's talk about the next one type of wind turbine. That is type 3, double fed induction generator. Right, okay, so um, on the right side, right, is a small picture of how this wind turbine look like in the various components, right? Okay, so as you can see over here, this is the rotor hub. Okay, so connected to the rotor hub are the blades. Yes, as you can see, to reduce the weight from this wind, utilizes um, most often three blades are required, and it allows the higher efficiency to be achieved. Because as you add more blades, basically, it's reducing the weight. You have a lot of wind area that is impacting on this blade. Okay, so connected to the blade is the low speed, shaft portion of the wind turbine, and the low speed shaft is connected to the gearbox. And like I made mention that what does the gearbox do? It multiplies the speed, 1,000 to 2,000 times. Then on the other side of the gearbox, we have the high speed shaft. Right, so after converting the low speed to a high speed through the gearbox, basically we are able to achieve the highest speed of rotation that is required by the turbine generator rotor to achieve provide or produce the required power. On this side is basically the controller, and uh, some of the controllers are also, downstairs, basically, on the tower. Then we have the anemometer, basically that's on the wind vane, basically, that's the wind vane, the direction of the wind, and also, anemometer, that senses the wind speed and provides the controls to the yaw and also the pitch spin. Then on this side, it's the yaw drive. Remember, I made mention that the yaw drive and the motors and associated motors is what helps to redirect these wind blades in a different direction when the wind speed changes, right? And this is the yaw motor, and this is the power factor, right? Okay, so now let's talk about. I've made mention. I've gone through thoroughly. What are the components of this wind turbine are, but let's it has control scheme, and gearbox system, and generator, and a stator, and a rotor, and the stator is directly connected to the ECU. We have a rotor that is also integrated to the grid through a back-to-back voltage of power electronic converter, and this is 30% rated, and the reason being that it basically helps us to achieve much cost reduction and also power losses. And basically, the converters on the road side, right? We have a road side converter or machine side converter, and basically that controls the speed of the rotor. And on the grid side, converter basically helps us to basically, export, the power or exchange active and reactive power to the grid, right? Okay, so if the voltage is applied to the rotor, right, it's basically its goal, like I mentioned, is to regulate the speed of the rotor and through a split frequency, and that helps us to achieve two components of rotor current, that is direct axis and quadrature axis current, and basically the quadrature axis and the direct axis based on the type of um, vector control scheme that we are utilizing. The direct axis can control the reactive power, and the quadrature axis can control the active power. Right? So um, basically, the variable speed, frequency voltage so that is applied to the rotor helps us to reduce the mechanical stress and achieve an overall efficiency and acoustical noise from the operation of this wind turbine. So now let's move on to what the advantages of this wind turbine is. Basically, this wind turbine has much better advantages compared to the type A and the type B or the type 1 or the type 2. Right? It has a strong capability, because of the power electronics, the back-to-back power electronics. It helps us to control or decouple the control of the active and reactive power, and basically, exchange active and reactive power, to the grid and also to the converter. And like I made mention, the power electronics only utilizes 30% of the required power, which basically is a significant cost saving. And with regards to the drivetrain, the mechanical drivetrain, it results in a mechanical lower mechanical stresses, and also the power and the voltage fluctuations are much lesser compared to the type A or the type B. Now let's talk about the disadvantages, right? Yeah, because of this type of wind turbines, definitely you have a lot of mechanical components. It has the gear system, right, and also split rings with the brushes for the on the generator side. So it requires a lot of maintenance, and that can be expensive embedded cost. Right? And it's subject to frequent faults, especially the gear system, and also when it is any disturbance on the grid can sometimes extend to this wind turbines, and has rotor current controllers that can be expensive. Now let's delve, take a deep dive into the schematics of this wind turbine and the controls, right? Okay, so as you can see over here, on this side is the wind turbine, and the wind turbine blades, and you have this wind that is basically impinging on these blades, right? Okay, so once the wind impinges on this wind turbine blades, it starts rotating, and this is the angular velocity of the rotation, right? Okay, so you have a shaft here, basically, a low speed shaft, that is connected to the rotor blade and rotor hub. Okay, so there's a hub here. And the low speed shaft is connected to the gearbox, right? And like I made mention, the gearbox multiplies the speed, the rotational speed, 1,000 to 2,000 times to achieve a higher. So this is the high speed shaft portion of the wind turbine, and that is connected to the rotor. The rotor has a winding, and basically, it has basically split rings, and the split rings have thrusters, right? Okay, so this is a round rotor industrial machine, and it has stator, So basically, the generator side has a stator and rotor, and basically split rings and a bit gases. Now the converters. Let's talk about the converters. We have the machine side converter, and rotor side converter. And like I made mention that the goal of the rotor side converter is to control the speed of the rotor through a split frequency. Right. Okay. So in between this back-to-back converter is a DC link, right? And a capacitor. What is the purpose of the capacitor? The capacitor is fully charged with charges to maintain the DC voltage, right? And on this side is the gate side converter, and its goal is to basically to regulate and regulate the active and reactive power exchange through the gate. And from there, it goes through a step-up transformer, right? Okay, and that sets the voltage from 690 volts to 36 kV AC collection point or 66 kV AC collection point. Now let's talk about the operational mode of this type of wind turbine. We can have over synchronous mode of operation, right? Okay, so over synchronous mode of operation. That is when the stator is exchanging active and reactive power with the grid, and the rotor side is also exchanging active and reactive power with the grid. And the synchronous operation is when only the stator is exchanging active and reactive power with the grid. And then again, the stator is feeding active and reactive power back to the rotor side. So these are the forms of operation of the wind double fed induction generator. Okay, so the next schematic diagram of the double fed induction generator basically helps us to understand much deeper into the controller, right? Okay, so similarly, I told you that we have the wind, wind power, with the wind velocity, basically hits the turbine blades, it starts rotating, and the gearbox multiplier, and rotational, velocity, and basically you have mechanical power from the wind turbine, and basically, it goes translates into electrical power, right? Okay, so the goal of the stator is to exchange, active and reactive power with the AC grid, right? Okay, and the back-to-back power electronic converter basically to exchange active and reactive power with a rotor, control the speed of the rotor, actually control the speed of the rotor through transformer action, through induction, from the rotor to the stator and back to the grid, right? Okay, so you can exchange, active and reactive power with the rotor, and the grid side converter can exchange active and reactive power with the utility as well. Okay, so we have a step down transformer that steps the voltage down so that the lower voltage can be utilized by this back-to-back converter. I think the voltage is typically about 690 volts, right? Or you can have a three-winding transformer, right? So the third winding that has a much lower voltage, 690 volts, can be utilized by this back-to-back converter, right? Instead of having a separate step-down transformer for this back-to-back converter, right? Okay, so the step-up transformer, right? What did I mention? For onshore wind farms, right, you have the step-up transformer that is located very close to the wind turbine, and its goal is basically to step up the voltage, output voltage from 690 volts to an AC collection voltage of 33 kV or 66 kV to the grid. Now let's talk about deep dive into the controls, right? Okay, so you can have a active power controller or reactive power controller. So these are the outer, controls that we have. Okay, this can be integrated through MPPT, and MPPT is maximum power point tracking. Okay, so at lower speeds, when the wind speeds are very low, that is when we utilize maximum power point tracking, and that is based on the tip speed ratio, which basically um, um, takes a look at chart and basically select the right active power and speed that is required to achieve the required power. So, integrated through the outer controls, that is the active power controller and reactive power controller, right? Okay, so you have the set point active power and the measured active power. And basically it goes to a PI input controller, and the error is created and it is fed here. Then you have the reactive power set point, and as the reactive power being measured, it goes to a PI controller, and the error is generated. Then from there, the quadrature axis rotor current is generated, and the direct axis rotor current is generated. It goes into a current controller, which generates the required direct axis voltage and quadrature axis voltage, which is basically fed into the power electronics, IGBTs to basically, correct the error. On the other side, the grid side converter. On the other hand, we have a DC voltage controller. So basically you have a DC voltage controller. You have a set point of the DC voltage, link voltage that it is supposed to control, right? Then it's the measured DC voltage. So these are based on measurement devices that are in the controller that sends the signal to this PI controller. And basically, the PI controller generates the error, and it is fed to this controller. And it generates the required quadrature axis current that is fed to this side of controller, basically, to basically provide a power impulse to the IGBT, and basically, to correct the required exchange of active and reactive power back to the grid. Now let's talk about the last type of wind turbine, and that is type 4 or type C. And we have a permanent synchronous generator, or we can have a wound rotor induction generator with a gear system. The permanent synchronous generator does not have a gear system. So that is the difference between these two types of type 4 wind turbines. Okay, so you have a choice of basically eliminating the gearbox, and to avoid this additional maintenance. And like I indicated, they have a back-to-back full scale converter. Then we have the absence of slip rings and brushes for the permanent synchronous generator. But for the wound rotor induction generator for the type 4, it still has the slip rings and the brushes. Then it's like I made mention, it can either be an induction generator or a synchronous generator. So for when it is a synchronous generator, it has a permanent magnetic poles, and these can be very many, about 84 of them, 100 of them. And basically, if you have many poles, what does it translate to? Much lower speed. But if you want a higher speed, then you go to the induction type. Okay. So full scale power electronic conversion, and basically that translates into higher power conversion, conduction, and friction losses. And like I indicated, the power converters allow for exchange of active and reactive, independent control of active and reactive power, and injection into the grid. And I have much smooth grid connection because of the absence of frequency. If you are utilizing the permanent control of generator, and the wind convention is very high, efficiency is very high compared to the double fed injection generator. But let's talk about these disadvantages. As much as we have many advantages of this type of wind turbine over the double fed induction generator, the full scale converters result in a lot of friction losses, and also the capital cost is very high right from the initial. But basically, it pays off with time. It has a high harmonics. You have a full scale power electronics converters, AC to DC, DC to AC, and they are full scale. Definitely, you're going to have a high harmonics, and definitely you require a harmonic filters to filter out these, harmonics. Then because of, especially this pertains to the permanent synchronous generator, you have a lot of magnets on the rotor. It can make you, the rotor very heavy. And matter of fact, the wind turbine very heavy. And if it is an offshore substation environment, basically, you're talking about a much weight on the offshore substation platform, right? Okay. Next is, a great picture, how the double thread induction generator looks like, Like I made mention, we can have a one rotor synchronous generator, and permanent synchronous generator or squirrel cage induction generator, So basically, if you have a squirrel cage induction generator that utilizes, a gear system, it utilizes split rings and brushes. And if you have a permanent synchronous generator, it just utilizes a magnetic pole. And you can have a one rotor synchronous generator that does not use a magnetic pole, but use a rotor that needs to be excited by DC. And the gearbox is optional, and that applies to square trading reaction generator. And this is a full scale converter that can be connected in a back-to-back configuration that is integrated to the grid. Now let's talk about the types of control schemes that we can have for wind turbines and matter of fact, double thread induction generator as a whole. And first one is push control, and the goal is basically to regulate the speed of the rotor, in terms of when there's a halt or and basically when there's a high wind speed, So we regulate the pitch angle on a longitudinal axis to increase the pitch angle, then basically we slow the speed of the rotor down. Then we have the yaw control, and basically this allow the turbine blades and hop to face the new direction of the wind speed. Then we have a maximum power point tracking, and let's say all of a sudden the wind speed changes to a much lower level, and basically you want to achieve the maximum power production output. So that is when you utilize maximum power point tracking. That's basically is able to select a particular speed and a particular power that is supposed to generate and basically implement that control scheme. Also, you can have the option of controlling the shaft mechanical stress by reducing the pulsation test on the shaft. Then the next control scheme is compliance, grid code compliance, where basically you have to regulate, and control the active power and the frequency that is being exchanged, and basically active power and AC voltage that is being exchanged with a grid. Next is the typical configuration of how an offshore wind farm looks like. How it is, all the components that it encompasses before it is power is exported to the onshore facility. Right. Okay. So you have a wind farm, consisting of many wind turbines that is arranged in different arrays, different configurations, and the most popular arrangement is radial or radial star. And sometimes, you can have a loop, for much more reliability. But, that itself translates into, higher cost, as you form those loops, redundancy, putting all those redundancy in is more cost. Okay, so basically, you have the export cable, right? Basically, you have a AC collection point that is integrated. All of them are daisy chains, and basically you have a common AC export cable that exports the power. Yeah, and, basically, you have a transformer here that sets the voltage up from a collection point to, let's say, from 66 kV to 30 kV AC, or 32 kV to 30 kV AC collection transmission voltage. So from here, then you have basically 230 kV AC export cable, transmission level export cable that comes here, and you have a converter here, right? You have a offshore converter that converts the AC power to a DC power conversion. Then from here you have the DC cables that are basically buried onto the ocean floor and positive, negative, and basically goes to the onshore converter that basically inverts, the voltage from DC to AC, and basically goes to a step-up transformer, right, from 230 kV to 400 kV transmission level before it goes to transmission power to the load center. Next, we'll talk about typical installation of an onshore wind turbine, right? Okay, so this is a typical pictures of how the onshore wind turbines are installed. As you can see, it's an excavation basically to create the required hole. Then basically putting cement in, typical cements are used, that has a very good excellent bonding power. And basically the structural elements are in place. Then another cement, then another structural elements are put into place. And also to support vibration. You have to accommodate for that and also exit. So these are all the structural elements that help to support. Let's decide, this is how the blades are transported, especially this is for onshore facilities, basically this is the blade. And this another form of transportation station for the blade, how it is transported, to the location that the wind turbine is being installed. And this section of the power of the wind turbine being carried through the various sections of the tower that is being installed. Next is a typical picture of on the left side is a typical picture of turbine blade, and as you can see housing. So this wind turbine is located very close to living space, so people are living. Then on the right hand side is a heavy crane. On the middle side of the picture is a heavy crane where a section of the tower is being lifted into place, and on the right side is shows you a picture of blade that has been installed. Next is a picture that shows basically the hub of the wind turbine. And this hub is where the turbine blades are connected. The turbine blades are connected on this side, one on this side, and one on this side. So forming three blades. Next is a picture of how the hub looks like. Like I made mention, the blades are connected on this side of the face of the hub. Right? Okay, one on this side, and on the other side. So this picture, middle picture shows the tower section. Because there are three sections that are installed, three of the sections, and this is one of the sections, and this is the next section. As you can see, people are standing here, and basically installing it. Next is, a nozzle. So this is how a nozzle looks like. If you've heard the buzzword nozzle. This is the nozzle, and the nozzle houses basically components of the turbine generator, the gear system, the low speed shaft, the high speed shaft, the generator itself. Next is a typical installation. We have the motor power installation. So this is a fixed bottom connection, right? And basically this power is basically driven all the way to the ocean floor, right? And you can have a jacket, so, right? You can have a three or four legs. It's basically same thing, fixed bottom, and this is all driven all the way to the ocean. And next is a deeper picture that shows you how the motor power configuration, is basically you can see this is the seabed, and it is driven all the way to the seabed. So a typical installation is what is called a fixed bottom installation. Next is as you can see, this picture shows how a floating wind turbine is being towed to its location. So this type of wind turbine is a floating type, and it's really for deeper depths. Usually more than 100 meters and above, and deep oceans. You want to opt for floating wind turbine. You don't want to use because it's too expensive to implement a fixed pattern. So I think the criteria for to install floating offshore wind turbines is for depth gauge and about 100 meters. Uh, so on the left side, top left side, as you can see, this is a structure. Basically this is the structure that supports the substation. So first of all, columns are pushed through the seabed. And I'll show you a picture of it how it looks like. And on top of that, this platform jacket is put on top of it. Then on top of it is basically this substation. So this is a typical substation where that is integrated to the offshore wind farm. So this is where you have all uh, your power converters, your HVDC transmission components. Next is a picture of a wind turbine blade, and as you can see over here, these blades are huge and massive, so as you can see, this is a tray wind turbine blades that is going to be transported to the installed. And this is a picture of a fixed bottom wind turbine that is located at an offshore facility. This is a typical picture of typical installation components, and I think this is one of the structural elements of, I think that is a part of the column, and that is being hoisted into place to be installed. Next is a picture of blades. So as you can see over here, we have six blades over here, right? So it means that these are going to be installed on two wind turbines. Each wind turbine is going to take three blades over here. I think this bottom picture, is a typical blade that is going to be hoisted into place. Then again, these are pictures of a turbine blade that has been installed. And on this side, this is another blade. It's been installed on the hub, and then definitely they are putting the hub into place. It's going to be bolted to the nozzle of this wind turbine, and this is the structural element. Next is basically the motor power and fixed bottom configuration. As you can see over here, this is how they push the structural elements all the way to the bottom of the seabed, and as you can see, they are pouring concrete through a ship to basically keep these columns into place. And so this is a wind turbine that has been fully installed, with the wind turbine blades. And this is the nozzle, and basically, this is where, basically a place when helicopters and choppers basically, bring personnel to work on the wind turbine. Basically, they come straight here, right? Or they can come by ship too, and go through the columns and up the ladder all the way up. Or they can, sometimes they can install elevators as well. Next is a picture of how these columns. Remember, I made mention about the columns, right? Where this the supporting columns. So these are the columns that are pushed all the way to the ocean bed, right? And they are that is done through controls. All the controls are done through a ship, and once they are pushed into place, one, two, three, or four of them, right? And after that, they add these columns on top of it, and that is what is going to support the top structure before the substation structure is put on it. Definitely, we need cables, AC cable, installation, export cable, and inter-array cable. Okay, so typical inter-array cables will be 6 33 kV or 56 kV before it goes to a collection point. Right? Okay, so these are the cables, how the cable installation are done, and we also have the DC cables. That is that basically, transports, the power from one converter, offshore converter to another converter that is located at the onshore facility. So this picture shows the inter-array cables, right, in between the wind turbine. They call them inter-array cables to the AC collection point. And this cable is basically a DC cable that is being hoisted into place and being installed, as you can see over here. The right hand side, next is another beautiful picture. On the right side, you have a substation that has been put into place, right? Okay, so this is a critical offshore substation, like I told you, that basically houses all the components of the HVDC system, right? The converters and all the controls, the transformers, and now basically these are all the supporting structures, and down below are the columns that have been drilled all the way down to the ocean floor. right? On the left hand side is the onshore side, right? Okay, so the onshore side also has its substation, and mostly they are air insulated substations, or it can be gas insulated substation as well, depending on then just how much money he wants to, and also maintenance and reliability. He can choose to opt for gas insulated substations if he wants lower maintenance cost and higher reliability and a lower footprint. On the other hand, he can choose to go with an air insulated substation if, let's say, he doesn't care much about maintenance, because air insulating substations you are exposed to elements, right? Okay, so basically this is the picture, right? And basically you have all the converters all here in bar hall. Next is another beautiful picture. That's on the left hand side is a typical substation, offshore substation platform that has been fully installed. As you can see over here, we have a helipad over here that helps helicopters to fly to this offshore substation, to perform the required, maintenance, operations, and even the waters, that's how they fly over there, right, through helicopter. On the other hand, they can also go by sea and, by boat. Basically, when they get too close to these substations, they are hoisted back on top to the platform. On the right hand side is a typical substation, offshore substation platform. Next is basically the type of protection schemes that we have for these wind turbines, right? Okay, so each wind turbine can have an inherent protection. So we have something they call rotor circuit protection, and that utilizes passive cover or active cover. Active means that it utilizes power electronics to achieve that purpose. Passive means that it utilizes passive elements to achieve that purpose. Okay, so what is its purpose, right? Okay, so when there's a fault, right? Be it a fault on the AC grid side, network fault, or in between the array of wind turbines, right? Okay, definitely, due to the unbalance that is created, right? There's going to be unbalance, and that unbalance is manifested in the DC link, right? There's going to be unbalance of active power and reactive power, and this unbalance results in excessive rotor speed, right? Okay, so and rotor currents, high rotor currents, and basically the goal is basically to utilize this crowbar by stopping the rotor, and basically this high energy from this high currents basically discharge to ground. This itself helps basically the wind turbine to ride through the fault, and after extinguishing that fault current. Next is rotor speed. It is able to control the speed and based on a certain set point. If the rotor overspeed due to a next fault or unbalanced fault, basically on overspeed to a certain extent. There's a set point that if the rotor speed reaches, it just basically shuts, disconnects, the wind turbine. Then you can also have individual under voltage, for voltage protection elements that's dedicated to each wind turbine. Now let's talk about the challenges of inverter-based resources. As you can see, we have a large penetration of that, and as these wind turbines, wind farms are being integrated to the existing AC protection grid. Basically, they throw us a challenge. And the first one, let's talk about reliability of the protection scheme. As you know, traditionally, we have synchronous generators, right? Okay, and These synchronous generators or hydro units have filling pole generators, and these basically provide a lot of inertia to the grid. These with a large mass rotating mass, okay, and also it provides short circuit to the grid, and this itself strengthens the short circuit capability of the grid, right? And when this fault, definitely, short circuit current is supposed to flow for this potentially relay elements to detect that fault. And due because inverter-based resources, wind farms and solar PV, lack that capability. They don't have inherent capability of providing short-circuit support to the grid. As such, there is a decrement of short-circuit capability of the existing grid. As these synchronous generators are being decommissioned due to basically the goal to achieve net zero and carbon reduction. As such, a lot of these coal power plants are being decommissioned, and these are many synchronous generators that basically provides inertia to the grid. In terms of this synchronous generators providing extensive inertia to the grid, it helps to strengthen the grid. In that, when there's a fault on the grid, basically, what happens because of that inherent inertia that this synchronous generators rotating mass provide to the grid, it prevents the rate of change of frequency. It limits that from being decreasing at a faster rate, right? On the other hand, these inverter-based power electronics converters do not have that inherent inertia to provide that to the grid. As such, when there's a fault, the rate of change of frequency can be very fast, you know, and very fast, and that itself basically requires mitigation schemes, and there have been, virtual initiatives that have been programmed and controlled, put into place to provide that virtual inertia to help prevent the fast decrease of the rate of change of frequency. Next is subsynchronous resonance. Okay, so this wind turbines have a generator, right? And generator has an inductance in it, right? Okay, so if you have a wind turbine farm that is in close proximity to a transmission line that has a series capacitors installed. Most of these utilities and generation companies, install series capacitors to basically increase the amount of power that is being transmitted. If you install a series capacitor, what does it do? It decreases the reactance of the transmission line. Okay, so the XL minus the XC, basically, as the bottom part of, the power curve, right? So power is equal to V1 V2 sine delta over X, right? So if you have an existing XL, that is the reactance of the transmission line, having a decrement minus xc of due to the installation of series capacitance. So overall, you have your the denominator, your x, it decreases. That basically helps to increase the amount of power that is being transmitted, right? As much as it is good to achieve this higher, power transfer schemes, it becomes very difficult for wind farms to be installed in close proximity to this transmission lines that have that facility of series capacitance. As such, it requires subsequent resonance studies to be done, and that will be part of the requirement, of the connection AC transmission utility. They're going to require you, and that will be part of the grid code requirement for you to perform the studies to make sure that you're not going to have subsequent resonance because of that. Next is the wind source. It's not reliable, and it varies. You know, so as such, it cannot be dispatched. Compared to conventional, power generation sources. Basically, gas turbines and nuclear power plants. Those are basically dispatchable. They can be dispatched because you can predict, its load. Okay. Next is, as with wind farms, you can have an island location, and you can also have it being connected to the grid, right? Okay. So when it is connected, you have a wind farm. When it is connected to the grid, right? The when there's a fault on the grid, the fault current that flows is about 5 to 14 times the nominal current. On the other hand, if it is connected in an island mode, right, the short circuit current decreases. It is about 25 times. As such, it requires an adaptive protection scheme that has to be implemented. So that basically provides the protection scheme for the wind farm when it is operating in an island mode, and similarly when it is connected to the grid. Next is directional overcurrent protection. It is required. Okay, so you have a wind farm that is arranged in array, right? So when a fault occurs on either side of, or different locations of the array arrangement, it's going to basically generate different magnitudes and different directions of a current. Okay, so this can cause malfunction of a current relay. So a directional overcurrent protection is required to be able to detect the direction of where the fault is coming, and basically isolate the wind turbines that basically show that vulnerability of the fault current. Next is lack of inertia, and I did mention of it that comparably they don't have inertia to provide to the grid persistence down the grid compared to synchronous generators that have larger rotating masses, that basically provide that inherent inertia to the grid. Then it cannot provide short circuit current. The short circuit current basically is limited. Matter of fact, it's a little bit of the nominal rating. You can have it as let's say 1.1, 1.2. That is how much for current. Because of the controls, the protection controls that is in place. Next, let's talk about fault right through techniques that you can have. And grid code requirement. And this is part of the grid code requirement, and that is what the regional entities and the utility transmission utility companies require. Okay, so you can have a temporary reduction of active power. When there's fault, that helps you to ride through the fault and get connected, stay connected to the grid. Then you can have a temporary reduction of active power, and also boosting your reactive power. You can have it boosting of reactive power through your power electronic controls, or uninstalled reactive component that is capacitors, or static power compensators, or STATCOM, static synchronous compensators. You can also utilize the crowbar circuit for the double-sided induction generator. I think I did discuss that about when you have a fault and there's a high current flowing through your rotor current. You want to prevent that damage to that rotor. So basically, you short circuit the rotor winding through the crowbar circuit. Then you have a DC chopper, right? Okay, so you have a DC chopper. When this side unbalanced fault occurs, right, it basically results in an unbalanced energy. That unbalanced energy on each side basically results in over voltage on the DC link. So how do you mitigate that over voltage? We use a DC chopper, right? Basically that, and for the DC chopper, definitely. Same like the crowbar, we can have an active DC chopper that utilizes power electronics, or we can have a passive crowbar, DC link chopper that utilizes passive elements. And basically, it dissipates all the energy and allows restoring of the nominal DC voltage. Then utilization of STATCOM and static power converter at the point of power coupling to provide the required reactive power that is needed to ride through the network fault.